All right, we have questions on the homework?
Yes.
Yes.
Oh, yeah, I thought somebody came in and verified all the answers from the other three people.
Is his name Anya Wu?
Is his name wrong?
No, his name is Lum.
I knew it.
Okay, which ones do we need to do then? All of them, not even number one?
None of them.
2C. Wait, what?
Oh yeah, 2C is right.
Okay, let's do number two.
No, just 2C.
Find the points on, this is so two-dimensional,
No, just 2C.
but we gotta do them all,
Why?
because they're all related, that's why.
What?
They're all related. Okay, so we got a position vector, and it says r and r prime, which is the velocity, are perpendicular. Oh, this is not the one then. Or maybe it is. So if two vectors are perpendicular, the dot product gotta equal 0. Okay, so what is r prime? 1, 2t. Find the points at which they have the same direction. So first of all, the dot product gotta equal 0. Wait a minute. Oh, this is part A. Find the points on this curve at which r and r prime are perpendicular. Oh, so the dot product gotta equal 0. So dot product t plus 2t plus 2t cubed gotta equal 0. Factor out a t, and you get 3 plus 2t squared equals 0. Am I making a mistake? Is that correct?
Oh, yes.
Okay. And of course, you're only going to get imaginary for this one, so that means when t is 0. So what are we trying to find? Find the points on the curve. So since this is the position vector, the point will be 0, 1. Just plug it into the position equation. That problem was kind of weak. If I were to put this on a test, I would make this one to get even more solutions. So this is A. Part B. Find the points at which they have the same direction or opposite direction. Now, if two vectors have the same direction or opposite, how do you determine if two vectors are parallel?
They're like scalar multiple.
Yeah, one is a multiple of the other. So that means this one has to be a multiple of that. In other words, this 1 gotta equal to a constant times t. Right? And then this one gotta equal to a constant times 1 plus t squared. And then you solve it. Two equations, two variables. You need me to solve it?
Just guess.
Guess and check? Oh, okay, what if I make the answer come out to plus or minus 1 over root 3 or something? Who's gonna get, I'll make it something even more exotic or even erotic. So what do you want to do? Solve for k in this equation? K equals 1 over t. Plug it into here. So 2t equal 1 over t, 1 plus t squared, multiplied by t, 2t squared equal 1 plus t squared. T squared equal 1. That's why you could guess and check it, because it just comes up plus or minus 1. Well, I'll be sure not to make it come up to something nice. So to thwart the guess and checkers. The guess and checkers. Thwart. Okay, now we can answer both questions. Find the points in which they have the same direction. Okay, now what happens when t is equal to 1? What is the position vector going to be if t is 1? 1, comma, 2. What is the velocity vector going to be? 1, comma, 2. They're pointing the same direction. But what about when t is negative 1? What happens? What is the position vector going to be? Negative 1, 2. And then what is the velocity vector going to be if you plug in negative 1? 1, comma, negative 2. Oh, wrong thing. They're pointing opposite directions. So when t is 1, they point the same way. But when t is negative 1, they point oppositely. But they're still parallel, right? Even if you're like this and this, and then that and that, they're still parallel, except one is pointing one way and the other one's pointing the other way, yeah. Park?
Sorry. Wait.
In order for two vectors to be parallel, one has to be a multiple of the other. So that's how you got these two equations right here. This gotta equal to a constant times, or you could have put this is a constant times that, it doesn't matter. One has to be a multiple of the other. So we're just doing them all then? Number 3. Now, look at this. R prime, this is the key right here. R prime of t is equal to a constant times
Oh, that's a constant.
Oh, yeah, I didn't know that one.
R of t. So this goes back to calculus last year. This is like the differential equation dy dt is equal to a constant times y. Right? There's like y prime and y, yeah? Okay, let's see if anybody remembers something. Cho, I know you know, right?
Wait, how did?
Oh, you even came in for help.
Wait, we're doing C?
We're doing 3 now.
Oh.
This is the answer for part B. This is the answer for part C right there. Okay, number 3. If you have this differential equation dy dt equal ky, what is the solution to this differential equation? Wang,
dy equals ky dt.
Oh.
Park. This was on the cheat sheet for PC calculus.
E,
Part-
Okay.
KY, E, K.
Oh, it's ha.
Y e to the k.
Oh, close. See, the solution is y equal y naught e to the kt. This
That's
is,
what I meant.
that's what you.
The Y
I
not.
was pretty close though.
I was very.
I know it had something to do with e.
I know it's Y.
Okay, so since we don't remember, we're gonna have to derive it. Okay, remember how? This is a good review anyway. You guys remember how to solve differential equations?
Oh, shit.
You separate the variables. You put all the y's on the left and put all the t's on the right. And the constant, it doesn't matter which side it's on, I'll just leave it on the right. Now we take the integral of both sides, integrate the left, ha.
One. No.
Say what?
Y. I don't know.
Wang?
Oh, then why?
Oh, sorry.
Oh, wait.
Part, integrate the left side of the equation.
Wait, why is it not?
Left side?
Oh.
It's
Oh,
natural
yeah.
log, absolute
Oh.
value of y, plus c.
Oh.
That's not the same thing! Are we getting this on video? Equals, how come I'm not writing the plus c?
Cause it mushed.
Okay, we're gonna mush the 2 plus c's together, that's why. Okay, you know what? We're in the embryo stage, plus c1 then. Okay, what is the integral of the right side, huh? Redeem yourself.
1/2 case.
No, no,
No,
no.
wait. No, no.
dt, t, this is a constant.
Oh, yeah.
Your variable is t. That's
Oh,
why.
KT.
Okay, kt, no,
Plus
plus
C,
c. And then what do we customarily do? We mush the 2 constants into 1 constant. Does that sound familiar? Mush.
Yeah.
And since y represents a population, it can't be negative, so no need absolute value. That's what Wang is going to say, right?
Yeah.
I knew that.
Yeah, I knew.
Y is always positive. Now, how do I get rid of the natural log? You e both sides. E to the natural log y is y. And then, isn't e to the kt plus c the same thing as e to the kt times e to the c? Because you add the exponents? Yes. And if c is a constant, then isn't e to the c power also a constant? And what do you think we call that constant? What do we call this constant?
Why is it?
Why not? Yeah, you can call it y sub 0, I guess, but we call it why not? Do you guys even know not?
Why not?
Yeah.
Okay, spell not. Huh?
KNOT.
Oh, not.
N-O-T. Oh,
Why?
N-A-U-G-T.
What?
N-A-U-G-H-T.
Is that right?
That's naughty.
I thought that's,
I don't know.
I don't really know.
Is it like in Shakespeare?
Come on, I had a 400 SAT verbal.
NAUGHT is a word.
Yeah, that is a
Yeah, I think it is,
It's
yeah.
in Shakespeare.
It means naughty.
Yeah, Yeah, it means zero, yeah?
It's
means-
like you not. No, you know what I mean? In
Yeah.
Shakespeare, it's.
Okay, anyway, that's where this thing came from. That's why in BC calculus we memorized it, remember? I told you whenever you see this differential equation, that's the solution because we don't want to reinvent the wheel all the time because this is a very important equation in calculus. Look how important it is. It came up in the homework. Oh boy. So, okay, we gotta go to the left side of the board because we're videoing. Oh man, if you could just remember what we learned in PC, we wouldn't have these problems, man. Or in PCH for that matter.
I actually don't remember that at all.
For real?
Oh,
Y equal Y naught e to the, there was a whole section on it in the book.
Wait, are you serious?
Exponential growth and decay. Oh boy.
You're not.
Here we go. So, and R of 0, these are your initial conditions, is 1, 2, and 3. So, what is your, we're trying to find the regular vector, right? It says find the curve. Okay, so what is R of t then? Knowing this, look, if the derivative of R is equal to a constant times R, this is the solution, right? This is the initial condition. So what do you say the x component is going to be?
1 e to the kt.
Yeah, but except in our problem, k is alpha, yeah? 1 e to the
Oh,
alpha t. What is the y component going to be?
2
2e to the alpha t, and then 3e to the alpha t. And there you go. So the hardest part of that problem is to remember this. No phone in
I'm
class.
taking picture.
Oh, good one.
I
Good
am.
one, Park. Oh. Okay, do we have to do number 4? Yes or no? Or are we just doing them all?
No.
Oh my goodness, Wayne said we're doing them all. R1 position vector is e to the t minus 1, 2 sine t natural. Hey, that means the people who are not in class are actually ahead of you guys then.
Where they are.
Yeah, because they came in for help last week and they asked,
Last week.
Because you told me.
oh boy, we're in trouble. U plus 1, u squared minus 1, u cubed plus 1, okay? And that's another position vector. They intersect at the origin, so that means they both pass through the origin. Find the angle of intersection. Now, if you have two curves like this, and they intersect, let's just say this is the origin right here. How do you find the angle of intersection?
Yeah.
The dot product of what though? We need the tangent vectors, and what tells you the tangent vector?
Velocity.
The velocity vector, the derivative. So if you find the derivative of this one there, go ba-da-da, and then if you find the derivative of that one there, then go wah, and then you just find the angle between those two vectors, right? We know how to find the angle between two vectors. So what we need is, let's just call it velocity then. Okay, what is the velocity of the first position vector part? Looking at this one, taking the derivative of each component,
UP.
e to the t,
2 cosine t.
2 cosine t,
1 over t plus 1.
1 over t plus 1. And then for the second, oh, I forgot to put the vector sign above it, minus 2.
Oh.
What would be the derivative of the second position vector, Wang?
1, 2u, 3u squared.
There you go. Okay, now we have to figure out at what value do they hit at the origin. So the first position vector, what does t have to be? Let's call this one then. What does t have to be so that it hits the origin? Look at that. It's kind of obvious. What do I have to plug in for t so you get 0, 0, 0?
0.
0. So t is 0. But for the second position vector, what is the, oh, it's the value of u, yeah? What value of u will you get 0, 0, 0?
Negative.
-1. Okay, so you guys see that? Because they intersect at the origin with 0, 0, 0. Okay, so now we got the times, or if you think of u as time. So at t equals 0, what is the velocity vector gonna be? Right here, plug in 0.
1, 2.
1, 2, 1. 1, 2, 1. And then at u equal -1, the second velocity vector, what happens when you plug in -1 into this? You're gonna get 1, -2, 3. So that's these two vectors there, and how do you find the angle between two vectors? You do the dot product thingy. Cosine theta is equal to the dot product of these two vectors. You guys remember how to find dot product?
Yeah.
Multiply the x components, multiply the y components, multiply the z components, all over the length of this vector, which is the square root of this squared plus this squared plus this squared, and then the length of this vector, which is the square root of that squared plus that squared plus that squared. Is that root 14? But it really doesn't matter because that's 0. So therefore the angle between the two vectors got to be 90 degrees. They're perpendicular. Yeah. Don't worry, I'll make it come out so it's not 0 on the test. And finally, the last problem. A particle traces out a curve. Here's the position vector, 2 t squared, t minus 1 quantity squared. At what time is the speed a minimum? So, how do you figure out speed? What is speed, by the way? The absolute value of velocity, right? The magnitude of the velocity vector. So we need to find the velocity vector. That's easy. 0, 2t, 2t minus 1. Did I do that correctly? So the speed then is equal to the magnitude of that. So that's the square root of this squared plus this squared, let's save some time, plus this squared. Oh, 4t squared minus 8t plus 4. Did I do that correctly? Did I do that correctly? Okay, so that simplifies to the square root of 8t squared minus 8t plus 4. What the heck? Let's factor out a 4. And so you get 2t squared minus 2t plus 1. Did I do that correctly? So what's the question? At what time is the speed a minimum? When will this be as small as possible? When will this, how do you find the minimum of any function? What did we learn in calculus? Take the derivative and make a number line, right? But do you really want to take the derivative of that? We don't need to come on. You know why we don't need to take a derivative? Because if this is going to be a minimum, then the inside of the radical got to be a minimum as well. And what kind of function is that inside the radical? It's a quadratic. It's a parabola that's opening up. Do we know how to calculate the minimum of a parabola or the vertex? What do we remember from Algebra 2? Negative b over 2a. The x coordinate of the vertex is negative b over 2a. So what is negative b all over 2a? What does that come out to? 1/2. So when t is 1/2, that's when it's going to be a minimum. Of course, if you wanted to, instead of doing negative b over 2a, you could have just said, well, this is going to be a minimum when this is a minimum. So how do I find the minimum of that? You take the derivative, which is 4t minus 2, and you make it equal to 0, so t equals 1/2. So you can get the same answer that way too, yeah? But then of course, that's just when the derivative of 0. You got to verify it's a minimum, yeah? How do you verify that it's a minimum? You make a number line. Let's see if you guys remember anything. Think of a number bigger than 1/2. 1, plug it in there, comes out positive, negative. So this means the function is decreasing and increasing. So there you go, that's a minimum right there. This is called the first derivative test, remember? What was the second derivative test? Let's just review, because it's going to come up later on. Because there's two ways to verify a maximum or minimum. The first way is the first derivative test. Remember when the derivative changes from negative to positive, that's a minimum. If the derivative changes from positive to negative, it's a maximum. But what's the second derivative test?
When it's like
First
greater than
derivative
0.
is 0.
Okay, very good. The first derivative is 0.
Second derivative is
And if the second derivative is negative, which means the function is concave down, then
It's a
you have a maximum, local maximum, right?
Yeah.
If the first derivative is 0 and the second derivative is positive, which means it's concave up, then you have a local minimum. That's called the second derivative test.
Yeah.
That's gonna come up later on, except it'll be in 3 dimensions. What? All right, what is, now today's lesson, oh boy, I think we're finding lengths of curves, if I'm not mistaken, which is a review. Yup, you're finding the length of, oh, this is fun. We're gonna do a lot of integrals tonight. Okay, let's review how to find the length of curve from BC calculus last year. Now, of course, there was a formula, and when you took the AP exam, you just memorized that formula. Do you guys even memorize the formula?
Yes.
Okay, here, let me test. Let's say y is given as a function of x. How do you find the length of curve from x1 to x2?
Oh,
Integral.
integral of x1 to x2, the square root of y. No, something the square of the dy dx.
Okay, dy dx squared.
1 plus. Oh yeah. Oh dx.
dx.
Hey.
Very good, you guys remembered something. Okay, but what if the function is given parametrically? T1 to T2. Then the integral is T1 to T2 part?
Square root of dy dx.
No,
Or what? Is that dy dx?
we're doing it parametrically.
Oh,
Okay, let's go back.
dt
What?
dt dx.
Oh gosh.
dx dt
dx dt
squared
squared.
plus dy
Plus.
dt squared.
Okay, there you go.
dt. Woo!
And then of course, okay, you know what? I think I'm gonna derive it again because I think you guys will have a different understanding of it because some of you last year it's just a blur. Yeah? Okay, let's say you want to find the length of a curve. So what we do is we zoom in on it like that. We zoom in on a very infinitesimally small piece. So if you zoom in on it, aren't you gonna just see something like that?
Yes.
It's almost like a line, not quite, it's like a line. And then, remember, this is infinitesimally small. How do you label this? It's a change in x, but it's infinitesimally small.
dx.
dx, that's right. There's a change in y, except it's infinitesimally small. dy. And then, of course, you can see what's going to happen when we go to 3 dimensions, right? dz, infinitesimally small. So therefore, what is the length of the hypotenuse right here? The square root of dx squared plus dy squared, correct? So this represents an infinitely tiny amount of curve right there. And then of course, then we're going to add up all of these pieces because that's what an integral does, right? It adds up an infinite number of things. But when you have an integral, you got to have a dx, a dy, or a dt outside the rat because it represents something, right? Although some of you probably didn't even write the dx or the dy or the dt, but you have to have it to do an integral. So I will do one of them for you. Which one you want to do? The dx, the dt, or the dy? dt. Okay, let's do the dt one. So how can I go from this to something that has a dt out there? How can I get a dt outside? Inside the radical, we're going to, this is like over 1, we're going to multiply top and bottom by dt quantity squared, like that. Because this will come out of the radical as this, what's the square root of dt squared? Absolute value of dt, but since it's a positive thing, boom, that's how you get the dt out there. And then, if you lift and separate, you're going to get the square root of dx squared over dt squared. Remember, lift and separate? dy squared over dt squared. And then let's put the dt there. And then since both of them are squared, boom, that's how you get that. And since both of them are squared, boom, you get that. That's how you derive this. That's where it came from. And then, of course, tonight it's going to be 3-dimensional. And of course, if it's 3-dimensional, it's going to be given parametrically. So what do you think is going to happen? Plus dz dt, quantity squared dt. So if it's two-dimensional, then you do that. Three-dimensional, boom, you do that. It's quite simple. Now, the only problem I can see you guys coming across is look at problem 1e over there. They give you the position vector, and it says compute the length of the curve from t equals 0 to 1/2. And it says estimate within 1/1000 using power series. What? And I'll tell you which power series they're going for, although maybe the one on the test I give you, maybe it's not going to be this one. I'm talking about the binomial theorem. So let's review the binomial theorem. A plus b to the n is equal to, I'll do the first term. A to the n plus, second term, Wang.
N minus one.
Okay, there's an n minus 1 in it.
B.
B. Okay, very good. Okay, next term, part.
N to this. Oh, plus one, sorry. A,
No.
minus one, sorry.
Over
Wait, what? Oh, N,
2 factorial. The power of A
N minus two.
goes down by 1. The power of B goes up by 1. Does that sound familiar? N minus 1, n minus 2, over 3 factorial. The power of A goes down by 1, down by 1, down by 1. The power of B goes up by 1. That's the binomial theorem.
Maybe it's about.
Yeah, I'm getting nowhere with you guys.
Good part. Maybe it's.
Okay, you're gonna have to use this on problem 1E. So what does that mean? I'm gonna have to do it on the board tomorrow.
No, we're gonna get it.
Yeah, it's a power series. Well, you find out when you expand it. When you expand it, it becomes a power series. And, no, let's just see. You guys gotta remember something from last year.
Okay.
Okay, so that's tonight's homework. You just gotta sit down and work these problems out now. That's the binomial theorem.